Okay, and we're going to write the word parallelograms here. Okay, so we did properties of triangles for a couple days. Now we're going to take a look at properties of parallelograms. So we're going to fill in the blanks here. I'm going to give you about 5 or 10 seconds to think. Quadrilateral. Polygon with, Keely? 4 sides. And it says draw an example. So anything with 4 sides would do. There's nothing special about it. Okay, as long as it's got 4, I'll try and make my side straight. Okay, there's a quadrilateral. Parallelogram. Wilson, what goes on the blank there?
Parallel.
That's why we call it a parallelogram. Whoops, parallel sides. So an example of something like that would be this. And I could mark the 2 of those as parallel and the 2 of those as parallel. Rectangle. It says it's a parallelogram, so it's just a special type of parallelogram. One extra condition. Right angles. So it's basically what we drew before. So the sides are still parallel. Opposite sides are still parallel. Okay, but now we've got right angles in here. Square. D?
Equal.
Okay. Equal, or what's the geometry word for equal? Congruent.
Congruency.
Okay. So that would look like this. Yeah. Now, mine doesn't look like a square, but if I come through and I say, you know what? I've got those right angles, it's a rectangle. And then I go through and I say it's got 4 congruent sides. Even if it doesn't look like they're congruent, then they are congruent. Okay. Trapezoid. Luke? 1 pair of parallel sides. So a lot of people draw trapezoids like this. They almost always draw trapezoids like wedge shapes like this. Don't forget that a trapezoid can be something like this. It can be standing up on its end. Okay, so the parallel sides don't always have to be horizontal. Drawing them vertically every once in a while is helpful. And then diagonal, segment that connects, non-consecutive. Got a hint there. I.e. means that is. Yeah. Close. Looking for a different word.
Okay.
Starts with a V.
Vertices.
Okay.
I was thinking that
Okay.
when I
Vertices.
second-guessed myself.
Yeah, there you go. Okay. So, again, we studied triangles. We talked about triangles. We looked at their properties. Another shape that we use all the time in geometry is a parallelogram. And there's a whole bunch of interesting properties for parallelograms. So there's some theorems about these. And we're just going to kind of lump them all together. And you can look up proofs for these and stuff like that, but here we go. So if a quadrilateral is a parallelogram, so if we've got a parallelogram, then, any ideas on that one? Blank sides are congruent. Yeah, 2 sides are congruent. Need a little bit more specific on here. What parts of this would be congruent? Yeah. Oh, like it. Okay. Opposite sides are congruent. So if you have opposite sides are congruent. So I'm going to mark it like this. Those 2 are congruent and those 2 are congruent. Okay. We know that for a fact. Now, it could be that all 4 of them are congruent and then we'd have a special type of parallelogram, but we know at least we've got that. Opposite angles. So we can mark here and here, and we can mark here and here. Okay, diagonals. I'm going to change colors for this. So diagonals. What do you think they do to each other?
Cross.
Yeah.
Intersect.
They do intersect for sure, but how do they intersect? What would they do to each other? Yeah. Kind of like that. Kind of like a center. Mason?
I think perpendicular.
Nope, not necessarily. Yeah.
Do they divide each other?
They do divide each other. How do they divide each other? They cut each other right in. Okay, very good. The word is bisect. So they bisect each other.
Gosh.
Okay. So what I can mark here is I'm going to go 1, 2, 3 here. 1, 2, 1, 2, 3 here. I'll do that last one. Okay. 1, 2, 3, 4. 1, 2, 3, 4. consecutive angles. So the ones that are right in a row, what would they be to each other?
Like supplementary.
Very good. What does supplementary mean?
Like adding to 180.
Add up to 180. So they are supplementary. Okay. All right. So we're going to take a look at one proof. Okay. Just one proof. Okay. So it says, look at this clever name. QUAD is a parallelogram. Okay. And we want to prove that QU, so this side right here, is parallel to AD. So this side down, or sorry, congruent. And DQ, so this one over here, is congruent to that one over there. So we want to prove the fact that opposite sides are congruent. Okay, so QUAD is a parallelogram, given. QU is parallel to AD, and DQ is parallel to UA.
I have an idea. Definition of parallelogram.
Perfect.
Let's go.
Okay, I find myself saying, if you're looking at a statement saying, well, no, duh, it's probably a definition of some sort. So definition of parallelogram. Okay. So here's what we've got. Those two are parallel, and those two are parallel. By definition, that's what a parallelogram is. Angle 1 congruent to angle 3. So notice that they did this. They drew an auxiliary line. That's what we call this, an auxiliary line, so that they could make angle 1 and angle 3, and angle 2 and angle 4. Then they're saying those are congruent. 1 is congruent to 3, 2 is congruent to 4. Wilson?
Opposite interior angles, or you can do vertex.
Let's see. Opposite, you're right. We use another word for it. Alternate. Okay? Okay, so these are alternate interior angles. So alternate interior angles. And we know alternate interior angles are congruent. So let's mark this. That one is congruent to this one. That one is congruent to that one.
So we're treating it kind of like a transversal?
Yeah, we are. That's exactly what we're doing. So let me make sure I point this out so everybody knows. What we're doing is we're treating that like a transversal. 2 and 4 are alternate interior angles for that one. And then if we look over here, 1 and 3 are alternate interior angles for that one as well. Good? Okay. Ooh, do you remember this one?
No.
Segment QA is congruent to segment QA. Okay, I remember making a video about this, and I remember saying, I wish I was in front of you because then I could show you. You could see it. A reflex, sometimes when you have a reflex, you kind of go like this. You kind of maybe hit yourself or something like that. Do you remember what it is? It's called the reflexive property. Okay, a segment is congruent to itself, so this is a reflexive property.
Yeah. Why do you have to show that?
Yeah, why do we have to prove
that? That is bad.
Okay, watch. Here's what we've got. So I'm going to mark this over here. We just said that QA is congruent to QA. So here's what we've got.
That's facts right there.
It's like saying my left hand is my left hand.
What?
Triangle QUA is congruent to triangle ADQ.
Yes, because you.
Think about it. Don't say it yet. The triangle up here is congruent to the triangle down here. D? Do we have angle side angle? We do. Angle side angle congruence. So angle side angle congruence. And the last one is a catchy little phrase. Not quite an acronym because you can't say it. You just have to say the letters.
It's a rock.
Mason?
Isn't it like the congruent parts of
Oh, yeah.
corresponding parts of congruent triangles are congruent?
Okay, so I wrote down CPCTC. Mason said corresponding parts of congruent triangles are congruent. So the corresponding parts would be QU and DA, and DQ and AU. So those would be congruent. The opposite sides would be congruent. Yeah.
So if that line going down the middle wasn't there, could you still solve it like that?
Listen up. Wilson just asked a good question. If the line, that auxiliary line that they drew there, could you still solve it? This is the easiest, probably the easiest way to prove this. I don't think there's a way that you could prove this without drawing some sort of auxiliary line or maybe external angles or something like that. I think you'd be stuck with something. I think this is the shortest way to do it. Yeah.
So in the second one, we do like the definition of parallelogram, and it's technically just number 6, like looked around in the end. Why won't we just like leave it at that?
Because she's got a good question. See how this one is really close to this one right here? Just we replace parallel with congruent. Because all this says is, guys, listen. All this one on number 2 says is that these two are parallel. It doesn't have any information about how long they are. They could be, I mean, they are segments, but we have no idea how long they are. Okay? And we want to show that they're actually exactly the same length. Okay, everybody good? Okay, we'll slide down here. Since rectangles are a special type of parallelogram, in addition to these other theorems, there's another one that applies. And that is if a parallelogram is a rectangle, then the diagonals are, what is it? Congruent. Congruent. Because if you think about this, I'm going to shrink this down just a little bit. With a parallelogram, if we take this and we kind of slant it a little bit like we typically draw parallelograms, one of the diagonals, the one from this lower corner to this upper corner, is going to get longer. The other one's going to get shorter. Think of taking a box and taking out the front and the back or something like that. You can kind of lay it down until this diagonals are super long and the other one's got hardly length whatsoever. Okay? If we make sure they're right angles, then they've both got to be exactly the same. So putting this together with number 3 up above, the diagonals are congruent and they, Lizzie, what else do they do to each other? Bisect. So what that means is, since they're exactly the same length altogether and they cut each other in half, what we've got is 4 congruent pieces. So if you take a look here, we've got a pair of isosceles triangles on the top and a pair of isosceles triangles that are different triangles on the side. Okay, everybody good? Okay, yes.
Can you just find base angles?
We would need more information to find the base angles, but yeah, there are some base angles here that would be congruent to the base angles up here, but we need more information to actually know what their measures are. Okay? All right, flip the page over. I'm just going to call on people, so be on your toes. Andy, can you tell us anything about those 2 angles? They're the same because they are opposite angles, and we know opposite angles are congruent. So 6b minus 10 equals 120. Add the 10. So 6b equals 130. Divide by 6. Let's see. Does it go in there at all?
No.
We can reduce it a little bit. 65 over 3. Is that right?
Mm-hmm.
Okay. Dane, can you help us out with this one? Tell us how to solve for y.
Let's see. So wouldn't like columns that are facing this way are the same, right?
They are, because diagonals always,
Like,
what was Lizzie's word?
Bisect.
They do. They bisect each other. So that means we can take 2y minus 5 and set it equal to y plus 7. And we can take 6z plus 1 and set it equal to 4z plus 9.
Yeah.
What Dane said. $12 for y?
Yes.
Ooh, this works out nice. 4 for z?
Yep.
Easy enough? Ouch. Lydia, any ideas on this one? If we know it's a parallelogram,
Yeah.
we have enough information that we could solve and find these lengths here. Yeah.
It's 22.
Opposite sides would be congruent. So those two things would be congruent. And wouldn't those two things be congruent?
I would believe so.
So which one do you want to solve?
The two, the left and right one.
Okay.
The left and right.
The up and down one.
Up and down for sure. So you're going to get x minus 3.5 equals 18.5. So you get x equals, let's see, 22. If you add the 3.5. Does it say we need to find the lengths?
No.
Nope. It just says find the value of the variables, right? Okay. Any questions there?
No.
Okay. Are we feeling better about this assignment than yesterday's assignment?
Yes. Very much so.
Oh, very nice. Okay. Find the values of A and B, or what would we need for A and B in order to make that a parallelogram?
Oh, so it's
Kind of the same thing. Keely, what do we, if this was a parallelogram, what would have to be true about this diagonal right here? Yeah, these two pieces would have to be equal to each other. So 3a would have to equal 4a minus 5. So a would have to be 5.
yes.
Colson, help us out on this one.
3b would have to equal 4b minus 21, and 3a would have to equal 8 plus 17.
Are they raised to powers?
No, those are degree symbols.
Why is it in parentheses then?
It's in parentheses because if somebody wrote 4b minus 21 degrees, they might think that those are two separate things. So it's the whole quantity that represents the measure of the angle.
I see.
Pretty good?
Yes.
B equals 21. And A would equal, over, that would be a 2A, 39. Anything hard about that one? Okay, opposite sides are congruent, so we'd literally just set the two of those equal to each other. So 2b plus 7 would equal 5b minus 8. And then we're almost done. Got b equals 5, right? Okay. All right, let's see. For example number 4, is the given information enough to prove, no for absolute fact, no matter what, that quadrilateral is a parallelogram? Keely, what do you think? Answer there is no. Okay, what, we could add one other piece of information. If they gave us this, then we'd be okay. What would it be? Yeah, the other diagonals. If they gave us that these other diagonals were cut into two congruent pieces, then we'd know that for a fact. Okay, so that one's a no. Gavin, how about B? So I'll put a yes. Can you give us a reason?
The opposite angles are congruent.
Opposite angles congruent. Perfect. So that's a yes, and there's a reason for it. Zach, what do you think about C? Is that a yes or a no? You think no? Okay. Not quite. Be careful.
It's close.
What do you think?
Wait, is it no?
No, it's a yes.
It's like, I think
But why?
How many
is
think
it-
no?
Wait. So sound.
How many think yes? Okay. Somebody who's got their hand up, tell us why you think it's a yes. What is it about this that makes it so that it would be a parallelogram? Yeah.
You can't have a shape with 4 congruent sides. It's not a parallelogram.
You think it's not, or you think it is?
But it is,
It is. How come?
because all the sides are congruent.
All the sides are congruent. More specifically,
Opposite sides have to be.
opposite sides are congruent. Now, this is a yes. opposite sides congruent. But I do want to point one thing out before we come back and take a look at that last thing on the back. Okay. This theorem, or these theorems that we kind of summarized here, they say if it's a parallelogram, then this has to be true. Every one of these has to be true. Each one of them independently, each one has to be true. What we're looking at right now is, hey, if I know that the opposite angles are congruent, does that automatically mean that it's a parallelogram? If I know that opposite sides are congruent, does that automatically mean a parallelogram? So the answer to that is yes. The answer to that is yes. Okay? So these theorems can actually be stated forwards and backwards. So the theorem is true, and the converse, the reverse of that theorem, is also true. Sometimes we'll hear them stated this way. It's parallelogram if and only if. So they'll put two ifs in there. And what that means is there's an if going this way and there's an if going the other way. Okay? So flip over on the back side. Little thought question to end there. Draw a square. Mark everything that's congruent. And on the diagonals, anything else? Angela. All the sides are parallel. That's true. We could mark that on there. The angles will take care of that because we've got same side interior angles that are supplementary, stuff like that. Can you think of anything else you could mark? Luke.
We could mark where the 90 degrees are. We could mark each individual angle. Many triangles that can grow.
So are you talking these little guys right here congruent? They are. Do you know how many degrees they measure?
45.
They do measure 45. So if that's the case, what I'm getting at is, wouldn't they do this? Wouldn't those be right angles also?
Yes.
And instead of having a rectangle where we've got a different size isosceles triangle on the top and the bottom, as opposed to the right and the left, what do you know about all four of those triangles? They're all congruent to each other. Okay? So last thought question is, what's the difference between a square and a rhombus? Difference between a square and a rhombus. Lizzie, what do you think? Square is right angles. So we've taken these sides that are all congruent and we've squared them up so we have this square. We've got 90-degree angles. All we have to do is push it over just a little bit to one side or the other. Then it becomes a rhombus. A lot of people call that a diamond or something like that. What do we lose? What do you lose if you take this and you push it over a little bit? Samara?
They're called the lines.
The diagonals. Very good. They're not going to be the same. So they're still going to bisect each other, but the diagonals are not going to be congruent anymore. What else do we lose? Yeah.
All the right angles.
Yeah, you lose all of those right angles. It's not right in the middle anymore. They're not all 90-degree angles. Those would change. So then we'd be back to more, okay, those would be congruent because they're vertical and stuff like that. Okay? All right. Any questions?
Can we skip one?